In this video, we're computing the moment of inertia of a solid ball, but this time the density of the ball is changing. So we're told the ball has a mass of m and a radius of big R, and the variable density is given by the function rho equals kr, where k is a constant and r is the distance from the center of the sphere. In other words, the density is linearly increasing from the center out. So the basic idea of the problem is that we're going to break this ball into nested spherical shells and use our prior result for the moment of inertia of a thin shell. So there's a representative shell with a mass of dm, a radius of little r, and an infinitesimal thickness dr. And we have a reminder of our prior result of the thin shell moment of inertia, and that's 2/3 mr squared. And the whole point of breaking it up this way is that the density has a single well-defined value at a radius of little r, and that allows us to express the mass of this shell using our density function. So just a quick reminder here about density. So density is mass per unit volume, and that means we can turn that relationship around and say that mass is density times volume. Well, for our thin spherical shell, we're going to use this equation in its differential form. So we say dm is rho dv, where dv is the volume of material in that thin shell wall. Again, restricting ourselves to a thin shell means the density has a well-defined value of k little r throughout that entire volume. So now we can sub in our density function, rho equals kr, and at the same time, we can write the volume dv as the surface area of the shell multiplied by its thickness dr. So making those two substitutions, we see that rho has been replaced with kr, and then dv has been replaced with 4 pi r squared dr. That's the surface area of the thin spherical shell multiplied by its thickness. Finally, cleaning up the expression for dm, we get 4 pi kr cubed dr. And now we're ready to start setting up our moment of inertia integral. So what we're going to do is say that the moment of inertia contribution of this thin shell, we call that di, is given by 2/3 times dm times r squared. That's just subbing directly into this thin shell formula, our mass of little dm and our radius of little r. So then we replace the dm with 4 pi kr cubed dr. Notice that when we do that, we can combine the r cubed with the r squared here and get r to the 5th. So this gives us 2/3 times 4 pi k r to the 5th dr. And we can clean things up a little bit here by combining the 2 and the 4 to get an 8 in the numerator there. And we get that di is 8/3 pi k r to the 5th dr. Now this di is entirely phrased in terms of the single variable r already, so we're ready to sum up these moment of inertia contributions by using an integral. So we say that I is the sum of all the di's. This is what an integral does. So we're adding up infinitely many infinitesimal contributions to get that total moment of inertia. And we sub in our expression for di, and that's 8/3 pi k r to the 5th dr. And we're summing up all these spherical shells as we go from the center of this ball all the way to the outer edge. So that's as little r goes from 0 to big R. Now this is a simple power rule backwards kind of integral. When I integrate r to the 5th, I just get 1/6 r to the 6th. So we have 8/3 pi k times 1/6 r to the 6th evaluated from 0 to big R. When we sub in the lower limit there, we get 0, so we're not concerned with that. And then we sub in the upper limit, which simply replaces the little r with a big R for the outer radius of the entire ball. And we're also going to go ahead and cancel a factor of 2 in this next step. And that leaves us with a 4 pi k over 9 times big R to the 6th. So we're not quite done yet because we want to express our final moment of inertia in terms of the total mass of this ball and the radius of this ball. And when we're done, it should come out to be a formula of this style where it's a constant times mr squared. So what we have to do is get rid of the k. And the way we're going to relate this k to m and r is by actually doing another integral. And this is a mass integral for the entire ball. So we're going to write big M, the mass of the entire thing, is the sum of all the dm's. And we have an expression for dm. That's 4 pi kr cubed dr. So we're going to add up all these mass increments as r goes from 0 to big R. And we get another power rule kind of integral here. We're integrating r cubed, which integrates to 1/4 r to the 4th. Well, that 1/4 is going to cancel the 4 that's hanging out here. And we just end up with pi k big R to the 4th when we sub in the limits of integration. Okay, so this means our k can be written in terms of m and r as m over pi r to the fourth. And now we can replace the k in our formula for the moment of inertia with m over pi times r to the fourth. So making this replacement, we have that I is 4 pi over 9 times k, which is m over pi r to the fourth, times r to the sixth. Now 4 factors of r are going to cancel, leaving us with an r squared in the numerator. And this pi cancels, and I end up with a final formula for the moment of inertia of this ball, and that's 4/9 times mr squared. And so we noticed that that's slightly bigger than the moment of inertia for a solid ball with uniform density. Remember that answer was 2/5 mr squared, which translates to 4/10 mr squared. In other words, slightly less than this result. If you enjoyed this video, or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.